Now, in this video, we're going to take up one more problem, the problem number 25. It reads as, draw the SFD and BMD for the beam shown in the figure, which is the overhanging beam, showing the intensities at the salient points. So we have at the point A, which is at the free end, which is having W, which is acting downward, and similarly at the point D, which is the end of the beam, at W, which is acting downwards. And between B and C, you have a simply supported, which is RBV and RCV, which is at a distance of L meters between B and C. Now, what we need to find out is to keep the body, keep the beam in the equilibrium condition. So we need to consider the static equilibrium condition. So we need to find out what is the vertical reaction, as the W is acting downward from both the directions. And also, you can see here, there due to the symmetry between B and A, the overhanging is A, and also from C to D, the overhang is A. Therefore, it will going to have a symmetrical distances. So therefore, by symmetry, what happens? Reactions at B will be equal to the reactions at the reaction at the point C. So how we can take it? RBV will be equal to RCV, which is equal to W, because on RBV to the left hand side you have W acting downwards. At RCV also we have W acting downwards. Both are the symmetric distance. Therefore, you will going to get that is equal to W. In other words, also you can calculate by taking the moments about the points B. Once you are taking moments about the point B, so RCV into L will be in the counterclockwise direction. Then also, since it is the moment about the point B, so that is again W into A. So W into A, and also that is equal to capital W into L plus A. So we have RCV into L plus W into A. So that will be equal to W into L plus A. So when you open the bracket, W into L plus W into A. So that means RCV into L plus W into A will be equal to capital W into L minus W into A. Capital W into L plus W into A. So as we have on the WA and WA and both on the left hand side and as well as in the right hand side, it gets cancels. So RCV into L will be equal to W into L. Therefore, RCV will be equal to capital W into L by L. That LL gets cancelled. So you will going to get RCV as W. Once you get the RCV as W, then what happens? Total load will be sum of the vertical loads on the upward direction is equal to sum of the vertical loads on the downward direction. So that means also we have RBV plus RCV is equal to capital W plus capital W. So that becomes 2W. So RBV, we don't know the reaction at the support B. So RBV will be equal to 2W minus RCV. So what is RCV? RCV is W. Substitute the value of RCV as W. So 2W minus capital W, which will going to be capital W. Therefore, RBV will be also having W as W. So this is how we can analyze it completely through the moments. Now we will going to consider the shear force diagram. Once we are considering the shear force diagram, so SF at the point A, suppose if you are taking the section, the section toward the left side acting downwards is negative. So SF at A will be equal to minus W. Between A and B, as there is no load acting upon them, therefore it remains constant at minus W. So when it comes to the SF at B, as we know, SF at B is acting upwards. So you will going to get it as minus W plus W, it becomes 0. So SF at B will be equal to 0. Then again, between B and C, as there is no other load acting on the beam, therefore it remains the same as that of B. Since SF at B is 0, therefore SF at C will also be equal to 0. That is between B and C is 0. So what will going to be the SF at C now? SF at C will be equal to, as the load is acting upwards, so it becomes positive. So that means plus W. SF between C and D, as there is no other load acting on the horizontal beam, so therefore it remains constant at plus W. And so this is how it will going to consider this, wherein you have SF at A is minus W, between A and B it is constant at minus W, SF at the point B is 0, between B and C is 0. SF at C will be equal to plus W. Therefore, between C and D, it remains constant at W plus W. So this is how you'll be able to analyze this problem using the shear force diagram. So when you're going for the bending moment diagram, here, so when you have the problem, so the bending moment at the point A is equal to 0. So bending moment at the point B will be equal to minus W into A. As the bending moment try to bend in the downward direction, it becomes hogging. So by convention in the bending moment diagram. So minus W into A. So then what is the bending moment at the point C? The bending moment at the point C will be equal to minus W into L plus A plus W into L will be equal to W into L plus W into A minus W into L minus W into A plus W into L. So on simplification, these two will get cancelled because minus WL and plus WL will get cancelled. So we're going to get the reaction. So therefore, bending moment at the point C will be equal to minus W into A. Now, what will going to be the bending moment at the point D? The bending moment at the point D will be equal to minus W into L plus 2A plus W into L plus A plus W into A will be equal to, so you are going to get it as on simplification. If you open the brackets, minus W into L minus W into 2A into W plus W into L plus W into A plus W into A. So WL gets cancelled because of positive and negative. So 2AW will be minus 2AW plus WA and WA will be equal to 2WA. So it will going to get cancelled. So it becomes 0. So this is how you will be having the bending moment at the bending moment diagram. When the bending moment at the point A is 0, so bending moment at the point B will be equal to minus W into A. Between B and C, it remains constant at minus W into A, and bending moment at the point D will be equal to 0. So this is how all the lines are joined by means of a linear line, as the power of x in the bending moment diagram is always x or the 1. So this is how you will be able to analyze and solve this particular problem. So as we see, the bending moment varies from 0 to minus WA according to the equation of the straight line, and it remains constant at minus W into A between B and C, and then decreases to 0. According to the equation of the straight line. So it is seen that the bending moment at the point B and C, it is seen that in bending moment between B and C, the bending moment is constant and there is no shear force. Hence, the portion BC is subjected only to the constant bending moment, free of shear force. This condition of B and C will be called as the pure bending. So this is how. When you have the pure bending, you are going to have only the constant bending moment and the pure shear force will going to be absent, or the free shear force is absent. This condition of the beam between B and C is called pure bending. So this is how you will be able to analyze and solve this particular problem. Thank you.